Okay.
All right. So, how is the differential equations going? How are undetermined coefficients? Not too bad. I mean, really, what you're seeing is that they're kind of algebra intensive,
Tedious.
and yeah, definitely tedious. And you still haven't seen like anything yet. In fact, what I'm going to show you today, I'm just going to do a little bit more about undetermined coefficients before we talk about some of the other techniques, because you haven't seen any that are really gnarly, because your forms, your forcing functions, or whatever you want to call those things that you're equal to, have been relatively nice. And worst case has been, ooh, we multiply by a t, right, kind of thing. But I want to show you how bad they can get. We're not going to solve these. We're pretty much just going to set up what the what form we would want to guess, and then kind of run with that. So, but I'm glad to hear that it's going okay. And I agree, Wes. They very much are like puzzles. It's just a matter of trying to figure out what it is. But as JP said, they do get really tedious though, because you got to find the derivative, you got to find the second derivative, you got to go through the whole deal, and it can take a lot of steps. So let me kind of generalize where we got and what the general forms are going to look like. And I want to add kind of to the list of what we should use as guesses, depending upon what that function looks like. So I'm going to go to the board real quick. And let's just kind of make a chart. And on this chart, we're going to be talking about anything that's of the form ay prime, y double prime, sorry, plus by prime plus cy equals, and let's just say that this is equal to f of t, right? Because it's all dependent upon what that f of t form is. So let's make a little chart. And on the left, we'll have f of t. And then on the right, we're going to put our guess for yp, like what we want to run with. So we've already seen, for example, if we have a polynomial. So the way I'm going to write this, when I write p of t, but with that subscript n, that just means it's n is the degree of the polynomial. Okay, so that way we can just be nice and generic. All right, so if we've got a guess or a forcing function that's a polynomial, our guess is another polynomial, right? And so we're going to write here, let's call it q. But I don't want to put just q, because there is the possibility that one of those things, or at least one of those things, is actually in the solution set to the homogeneous, right? Like if r equals 0, if we ever get an r equals 0, we know that there's going to be a t in there. So if we get a repeated, we need a t squared and so on. So what I'm going to do is I'm going to say, well, we need to multiply that by t, but I'm going to put a power s. And really the reason I'm doing this is to allow for when we get to higher order. Because right now, just with second order, we know that it'll never be more than a t squared, right? It might be a t squared if it's repeated twice, right? But we're just going to leave that. So polynomials, we guess polynomials. Same deal if we've got an exponential. So right here, e to the alpha t. We know that our guess is going to be some c e to the alpha t. And again, multiplying by some sort of t to the power if necessary. So that one. And then we saw if we have cosine or sine. And I'm just going to put cosine on my chart to save space. but we know that it's also true if we have sine of that. And so the guess here is going to be an A cosine of beta t plus B sine of beta t. And again, multiplying by some sort of t to the s. All right, so those are all the forms we've seen so far. And by superpositioning, we can actually have combinations of these, and our guesses are just going to be the combinations of their guesses, right? So if we had some sort of an exponential plus a sine, our guess would be a generic exponential plus this generic cosine and sine, and so on. Okay, but let me just show you some other variations that we can have that are kind of based on these. Like, what if we have a polynomial times an exponential? So we've never seen one of these, but if you have this, the general form, again, we're going to have the t to the s if necessary, but then the general form of this is going to be a polynomial of that same degree times e to the alpha t. And that should make total sense, because when we do the product rule on these, we're always going to get an e to the at. And from our product rule, we're going to get things of largest degree on down. So this will ensure that we can get the biggest degree as long as we match them. And then we have something similar if it's a polynomial times a trig. So if we've got polynomial times trig, we're going to do exactly the same thing, except we're going to have that polynomial times the a cosine b sine. And it's really for the same reason, right? That the product rule, as we differentiate, the degrees can only go down, and the cosines and sines just alternate. And so then the last thing that we could kind of do with these is, what if it's all three? What if it's a polynomial times an exponential times a trig? Well, then your guess is going to be a polynomial times the exponential times the trig times your t to the s. So these are the nice forms for us to recognize. However, they can lead to horribly big, nasty systems depending upon what that forcing function is. So I just want to do a couple of examples, just two examples here, to show you how big these can get and how bad they can get. So let's start with this one. All right, so let's say we've got y double prime minus 4y prime plus 4y, and that equals 2t squared plus 4t squared e to the t. And let's add on a trig piece as well. How about t times sine of 2t? So all I want to do is get this thing set up, figure out what our particular solution guess should be. We won't bother finding the actual solution. Okay, so where do you think we should start? What's the very first thing you should do anytime we're trying to do this undetermined coefficient stuff?
Find the homogene.
Okay, so Will's saying get the first and second derivatives. Brennan's saying find the form that we need. We actually want to do something before that.
Factor out a t.
No, don't want to factor out a t. I mean, we could. But this is something we should do no matter what this stuff is.
Find the solution to the homogeneous.
Yeah, we got to get the solution to the homogeneous first. Okay, A, you're going to need it, right? We're going to need to include that in our general solution. But why is it absolutely important to do, even before we try to guess the form?
Because that's going to get you the known set without, so that you can eliminate certain sections depending on. It's just to make things a little bit easier when you're trying to find your particulate.
I would argue that it doesn't necessarily make it easier, but it tells us if any of these forms are actually part of the homogeneous. And so then do we need to multiply by a t, or a t squared, or a t cubed, or whatever, right? So we definitely need to find that solution to the homogeneous to then make sure that we're using the right form. All right, so Bren just said that's what he meant to say, and that's cool. I know it's sometimes hard to translate our thoughts into words, so. But let's build this real quick. So we're going to have r squared minus 4r plus 4. And that thing is going to factor. It becomes r minus 2 squared, which means we get r equals 2. So it is repeated. So what are our solutions here?
E to the 2t plus t times e, or yeah, t times e to the 2t.
There you go. So the fundamental set, one of them is going to be e to the 2t. The other one's going to be t e to the 2t. So repeated roots, we just form the second one by multiplying by 2. Okay, so now let's see what our guess would look like. All right, so for this one, let's start with that 2t squared. So we know we're going to need a polynomial of degree 2. So we'll have a generic at squared plus bt plus c. So that takes care of the 2t squared. And it had nothing to do with any of the roots, so we didn't have to worry about it. So there's that piece. Okay, so now let's add on to that what we're going to need for the 4t squared e to the t. Okay, so let's just start with, in general, what would you need? Since we have a polynomial times an exponential, then that's going to be a d t squared plus et plus f, and that's going to be multiplied to e to the t. And luckily, that's not the same root or the same function as our fundamental set had in it. So we're good. So that's this piece. And then if we go down to the last bit, that t sine of 2t, that's going to require a linear function. So gt plus h times, well, for sine, what we need is a I cosine of 2t plus j sine of 2t. All right, so check that one out. How many unknowns do we have?
Too many.
Yeah, too many is the right word. I think it's 10. So we actually have, it's either 10 or 11. 3, 6, 7, 8, 9, 10. Yeah, so 10. We've got 10 unknowns. So think about how horrific this one's going to be. No, the next one's because of that. Let's just ask if I'm punishing everybody because he's in this class. All right. No, if I was going to be mean, I'd actually make you go through the whole thing and find out what the letters A through J are. But I'm not that mean. All right. Now, what if, let's just say, and I know that wasn't the case, but what if this had been 4t squared e to the 2t? So let's just say that that had been the case. So obviously, this e to the t would have to turn into an e to the 2t as well. But now we're in that situation where some of these things are actually part of the fundamental set, right? Look at this polynomial, the blue one. We take that polynomial and multiply by e to the 2t. These last two terms, they're actually part of that fundamental set. Okay, so that's a problem, right? So this is where we'd actually have to multiply by some sort of a t. But I want you to notice that t itself is not going to be enough. Do you see why that's a problem, or why it's not enough?
Because that's also already in the solution set.
Yeah, if you look at the last one, now the first one and the second one are fine. We're going to get a t cubed e to the 2t and a t squared e to the 2t, and neither of those are in that set. But the f is, and now we're going to get f times t e to the 2t. So this one we'd actually have to multiply by a t squared. So basically the way to think about it is just keep multiplying by t's until everything in your guess is new. It's not part of that fundamental set. All right, so there's that one. So let's just look at one more. Again, this will help us in terms of just get an idea of how to build these. All right. So let's say this is the differential equation this time. We're going to have y double prime plus 3y prime plus 2y. And let's make that equal, let's say, e to the t times t squared plus 1 times sine of 2t. And let's add to that 3e to the minus t cosine of t. And then add to that 4e to the t. All right, so our goal again is let's just get a form for the particular. So like before, let's go ahead and solve this thing, the homogeneous at least, so we know what the fundamental set are. So we're going to get r squared plus 3r plus 2 equals 0, which gives us r equals -1 and r equals -2. Just going to save us some time, which means our fundamental set are e to the minus t and e to the minus 2t. So we just need to be aware of those and see if any of them pop up. All right, well, let's start building this sucker. So for the first piece, we'll do this one in blue. Notice that we've got an exponential times a polynomial times a sine. So that means that in our particular solution, we need to have some polynomial of degree 2, so at squared plus bt plus c, times e to the t, times what we would need for the general sine, which is going to be a d cosine of 2t plus e sine of 2t. All right, so there's that one. That's by far the worst one because it's big and gnarly. All right, well now let's go to the second piece. So this one's an exponential times a cosine. So for an exponential times a cosine, we're going to take that exponential and we're going to multiply it by the f cosine t plus g sine of t. However, we've got e to the minus t. And remember, e to the minus t showed up. So what are we going to multiply this by?
E.
So you guys good with that? Just multiply by t. Okay, turns out we don't have to multiply by anything. I caught you. So why not? Why don't we actually need anything here?
Because there is none on the original bit, or?
It's because of the cosine and the sine. The actual function we get here is e to the minus t times cosine of t, which is linearly independent from e to the minus t. It's a different thing. This would have come from a complex root, right? That would have come from the complex root -1 plus or minus I. So it turns out that this is fine. Just because the e to the minus t is in here, it's not the entirety of those functions. So that one's actually good.
But the other bit, that's the issue. Or
The
no.
last one.
Yeah.
So if we go to the last one, the 4e to the t, that suggests we need some sort of an h e to the t.
Which isn't a part of the original set because it's it has a positive exponent.
Right. E
Got
to
it.
the plus t is not the same as e to the minus t, so that one's actually fine as well. So this one actually only requires 8 unknowns. So I guess, yeah, the last one was the punishment for Wes being in the class. This one's not so bad. It's only got 8. Yeah, except having to actually find them. I mean, think about what we did. We would take this guess and we would put it into the differential equation. So you're going to have to differentiate it and then differentiate it again. Just think about that blue part. Have some fun with the product rule on that.
You need so much data also on top of that. It's just a mess.
Yeah. Well, you're going to be able to get all of it without any extra information because you're going to know what all the different need to equal, right? Like if you look at the t squared e to the t sine 2t, it's going to need to have a coefficient of 1. So whatever all the different things are has to equal 1. You'll know the t part has to equal 0, the constant part has to equal 1. That's already 3 equations that will take care of 3 of the unknowns, right? And so on and so forth. So you'll always have enough information if you build it properly. Where you might run into trouble is when you forget to multiply by a t, or like a t squared in that other example, because then you might not have enough equations because you've lost some of the information. So as long as you're multiplying by the right powers of t, if there's repetition, you're guaranteed to be good. All right, so if I'm really feeling mean sometime, I'll make you do one of these by hand, but I won't. All right, so undetermined coefficients, I just wanted to show you these so you could get a feel for how to build the more complex structures, but it really is the same process as before. You make your guess and then go. All right, so let me show you another technique, another way that we can solve these things, these functions, and make life a little bit easier for us if we already know something. So this next process is what we call reduction of order. And you can actually apply it to any kind of linear second order. So I'm no longer going to require that we've got constant coefficients. All right, so now I'm going to allow these things to change. There can even be something in front of the y double prime. I just have to divide it out, and then it'll look like this. All right, so this is a little bit more robust because we're not going to be as restricted. However, there is something we need to know. All right, we need to have some function y1 that's a solution to the homogeneous. So even though this can apply to more types of functions, this is actually kind of a big deal, right? Having to know one of the solutions. Well, okay. But what's beautiful is that if you know one of the solutions, we can actually move forward. So here's what we're going to do. We're going to do the same damn thing we've done every time, where we go, all right, if I want to find us another solution, say y2, I'm going to assume that it's some multiple of y1. Now, this y2, like if it were the case of equals 0, that would be your second function in the set. When it's equal to ft, where ft is not 0, it's still that second solution. But let me show you why we don't even really think about it that way. So let's just kind of follow what would happen. So this is our y. So I'm just going to call it y for right now, so I don't have to write as much stuff. So then y prime, I got to use the product rule. Right? And then y double prime, I use the product rule again. So you can just take my word for it, but that's what those are. Hopefully you've seen enough of these by now that you notice the form. Okay, so if we put this in, check out what happened. We get u double prime, like we get this thing. So we get the u double prime, y1 plus 2u prime, y1 prime plus u y1 double prime, plus p times u prime y1 plus u times y1 prime, plus q times our original, which is u times y1. So that's what this thing's going to look like. And what I'm going to do is just regroup them. And I'm going to group them in their multiples of the u's. So we're going to get, say, y1 times u double prime. That's the only one that has a u double prime. The u primes, I've got 2 y1 prime. And then I've got a p times y1. And so that's all going to be times u prime. The u's, the pieces with the u, we're going to get y1 double prime plus p times y1 prime plus q times y1. So this equals f. So that was just a bunch of algebra to kind of get everything matched up. Okay, so I've got my multiple of u double prime, my multiple of u prime, my multiple of u. But this is where life gets easier. Look at this set that's in the parentheses that's multiplying to u. So notice that what this is, that's taking y1 and putting it into the original differential equation. And what we know about y1 is it's a solution to the homogeneous, which means all of that is actually equal to 0. So that piece is just going to go away. So let me take that away. And what we now have is y1 times u double prime plus 2y1 prime plus p of p times y1 times u prime equals f of t. So I know it probably doesn't look like much, but what I'm going to do is I'm going to put in another variable. I'm going to let z equal u prime. Because if z is equal to u prime, then u double prime is equal to z prime. And by putting that in, this equation is now y1 times z prime plus 2y1 prime plus p times y1 times z equals f of t. And take a look at this differential equation. Remember what the unknown is z. This is now first order linear. And I know I'm not seeing most of you on camera, but I can just imagine what I'm seeing there are really big smiles. Because even JP and Thea should be giving me really big smiles now. We should all be happy here. Why?
We can use our techniques that we know on first order linears on this.
Yeah, we know how to solve first order linears. So what we just did is we took a differential equation that had been second order, and we turned it into a differential equation that's first order. Hence the name, reduction of order. We reduce the order from 2 to 1. And so now it's business as usual, right? We divide by the y1, and we take this thing, we integrate it, we make it negative, we take e to that power. That's our integrating factor, yada, 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 yada. Okay, so this process is really useful. However, it does require us to know a solution. So let me show you. Let's do an example of one, and you'll see how the process works. But again, it's dependent on us knowing a solution to the homogeneous, because without it, we're toast. So let's try this one. Let's say we've got 2t squared times y double prime plus 3t y prime minus y, and that's equal to t. All right. So the hard part's going to be this. It's going to be looking at the homogeneous. Can you tell me a solution to this? Because without that, we can't go anywhere. So does anybody have an idea of what kind of form we might want?
I mean, to start out, you could divide 2t squared on both sides to try and get it into more of a workable form.
Okay, I can do that for you. Let's see. So we get y double prime plus 3 over 2t times y prime minus 1 over 2t squared times y equals 0. Does that help you see what kind of form we need for y?
Can't we then use that second order technique when it's a variable multiplier? Or
What technique do you mean, Thea?
where you let, oh, shoot.
All right, so you can see this is the hard part, right? So I'm going to help you. Because these are challenging. Turns out this is a nice function. We can actually just use y1 equals 1 over t to the minus 1. Because think about what happens when we multiply or differentiate. You can get t to the minus 1, it goes to t to the minus 2. So if we have t to the minus 1 divided by t squared, that's t to the minus 3. T squared t to the minus 2 divided by t is t to the minus 3. You differentiate again, you get t to the minus 3. So not easy, but if we find it, then we're actually good to go. So watch what happens. We let y1 equal 1 over t. Probably easier if we think of it as t to the minus 1. Then what we're looking for y2, right, or we'll just say y is going to equal some u times t to the minus 1. So y prime is going to be u prime t to the minus 1 minus u times t to the minus 2. And then y double prime, that's going to be u double prime t to the minus 1. We're going to get minus 2 u prime t to the minus 2. And then we're going to get plus 2 times u times t to the minus 3. So this middle term combines one of each of the product rule pieces that are identical from those two. All right. Well, let's plug this back up into our differential equation so that we can turn this into a first order. So we'll take 2t squared times this stuff. So that's going to give us a 2t u double prime minus 4u prime plus 4u times t to the minus 1. So that was the 2t squared times y double prime. So then we're going to add 3t times y prime. So that's going to give us a 3u prime minus 3u t to the minus 1. And then lastly, we're going to subtract y. But as expected, these things all cancel. They always do. So what we now have is 2t u double prime minus u prime equals t. All right. So now we get to do the reduction of order. If we just let z equal u prime, then this now turns into 2t z prime minus z equals t. If I get it into the form we like, z prime minus 1 over 2t times z equals 1/2. This is something that we can now solve for z. So let's go ahead and do that. Let's remind ourselves how that works. So we're going to get z1. It equals e to the negative integral of minus 1 over 2t so that's e to the integral of a positive 1 over 2t, which is going to give us e to the 1/2 natural log of t, which is the square root of t. But then we actually need to find z, because we know, I don't want to call this u, let's call it mu. We know mu prime is going to equal 1/2 divided by the square root of t. So that's 1/2 t to the minus 1/2. So we need to integrate that. So we get mu is equal to t to the 1/2. So then plus c. So we get z is going to equal t plus c square roots of t. And so that's the solution to this purple differential equation. Assuming I did all the steps right. Okay, well that's great, but that's just z. So remember what z is. Z is u prime. So let's go back to that. So we've got u prime equals t plus ct to the 1/2. So we need u. So u, of course, is going to be t squared over 2 plus 2/3 c t to the 3/2. But I need to add on another c. So I'll call that guy c2. All right, so u is equal to t squared over 2 plus c1 t to the 3/2 plus c2. The 2/3 times an arbitrary constant is still arbitrary, so I'm just going to call it c. Okay. But we're still not done. Let's try to remind ourselves where we are. What was the whole point of this u?
To solve the original differential equation.
Yeah, what do we do with this u?
Wasn't u used in order to find the second y2 is equal to y1 times u.
Yeah, so Brandon just put in the chat also u times y1. So we're going to take that and we're going to multiply it times y1. So because it was long ago on my board, y1, let me remind you, was t to the -1. So we're going to just take those and multiply them. And so we get y equals t over 2 plus c1 t to the 1/2 plus c2 t to the -1. And I want you to notice that this was even a little bit stronger than just finding the y2. I mean, the y2 is in here. You see the y2?
You also find the particulate also?
Yeah, we found a particular solution. So this was our y1. T to the 1/2 is y2. So there's another function that will actually satisfy that original differential equation. If you take the square root of t, you'll see that you do get 0 when you add it up. But we also found our particular solution, t over 2. And so this all by itself is the entirety of the solution. It's a particular plus the linear combination of our fundamental set. So reduction of order is even a little bit stronger because it'll get you all the way However, you gotta know y1. Without a y1, you're sunk. And it's not always easy. It's not always easy to look at something and figure out what y1 is. But if you can find it, reduction of order is an awesome, awesome way of going about this. This is something we're going to continue to see when we get to higher order. So third order, fourth order, fifth order. It's going to be the same kind of deal. If you know one of the solutions to the homogeneous, you can reduce the order down by one. And every time we do that, we turn it into something that's easier to solve, something that we have techniques for. So there you go. All right, so there's a lot of work to these, just like all the other methods. But the key again is you got to know y1. All right, so what do you guys think about reduction of order? Yeah, it's all right. I mean, it is algebra intensive, which is why I'm not going to show you another example because I don't want to spend the time doing all of that. But welcome to monkey math, right? It's the same process every time. You just got to know one of them. All right. Well, yay, that's great. But again, it requires us to know a solution, and we don't always know a solution. We can't always find one. I agree, Wes. He just said in the chat, we need a parody of the Monster Mash. They call it the monkey math. I'll let you get on that. I don't have time right now, but I look forward to hearing it. All right, so reduction of order, yay. But I want to show you another technique that always works or is always attemptable. You're going to see that sometimes the forms that we get, it's going to require an integral that we may not be able to do. But this is more robust. It will totally work for all of the undetermined coefficient things. But it's going to work for other kinds of forms of functions where it's not really apparent what kind of guess we need to use, and can be faster than reduction of order. Okay, so this one's called variation of parameters. So let me show you how this one works. All right, now variation of parameters does require knowing solutions to the homogeneous. So before I throw this out as the end all be all, it does require knowing both y1 and y2. So I just put here, it requires knowing the fundamental set. So in a situation where you can apply variation of parameters, you can also apply reduction of order. Okay, because we just saw that if you have one of the solutions, you can do reduction of order. This one's just a little stronger. We just happen to know both. Okay, so this is a thing. However, it's going to allow us to do or find a solution, even if that function that we're equal to is crazy. Like, for example, we'll just go with one that's not terrible. But like, what if I gave you something like y double prime plus 4y equals, let's say, 3 cosecant of t. Now, if this had been a sine of t or a cosine of t, you already know what to do. You make your guess, see what happened. But we can easily figure out the fundamental set because of the fact that it's got constant coefficients, right? So you can probably just look at that and tell me, maybe not, but can you tell me what y1 and y2 are?
Oh, that's a mess. Oh, that's plus or minus.
So it would be r squared plus
Oh.
4.
Yeah.
So plus or minus 2i. So what are we going to get if the roots are plus or minus 2i?
It's going to be that big long string of the exponential times the, well, if the exponential times the trig functions.
Okay, except we don't actually need the exponential.
Oh, because of, got it.
It's
Because
0
of the a.
plus or minus 2i. So this is just cosine of 2i, or 2t, and sine of 2t. All right, so maybe it's not quite so obvious for you guys yet, but we can find them. We know we can find them. So in a situation like this, variation of parameters is definitely an option and is a really strong option because, well, A, I don't want to go through all the algebra to reduce this thing in power, right? I don't want to reduce the order. And I certainly can't make a good guess for my particular, right? Because cosecant, you know, when you differentiate cosecant, you're going to get cosecants and cotangents, which then are going to give you a product rule and blah, 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 blah. And Lord knows what this would look like or what form we would need to take on. Okay, so we got to be in this sort of situation. Well, if we know y1 and y2, and we'll come back to this example. We'll actually work this one out using variation of parameters. But if you know y1 and y2, here's what we're going to do. We're going to start by making a guess, like we always do. And we're going to guess that the particular solution is going to look like u1 times y1 plus u2 times y2. So the same idea of integrating factors, I'm just going to have two integrating factors. There's going to be the one that I multiply to y1 and the other one that I multiply to y2. Okay, so we're going to make this guess, but we're also going to make another assumption about u1 and u2. Already, we're saying that u1 and u2 are such that this is true, that this product is a solution to the particular solution to the differential equation. We're going to make one more assumption. So we're also going to assume that u1 prime times y1 plus u2 prime 2 prime times y2 equals 0. So why I'm going to assume that, you'll see in a minute. But let's start with the why we can assume that. So u1 and u2 are completely arbitrary, right? And so we can impose conditions on them. And we can impose at most 2, since there are 2 functions. So the 2 conditions I'm applying are this one about the derivative times the original, and that they are actually the ones that give us this particular. So it's totally legit. We can definitely do it. You'll see why we do this in just 1 second. Okay, so U1 and U2 are not only going to give us this particular solution, but they are also going to satisfy this. We're going to restrict it a little bit. All right, well, watch what happens. We're going to take this and go and plug it into the original differential equation. So we need its derivative and we need its second derivative. So this yp prime, that's going to be u1 prime y1 plus u1 times y1 prime plus u2 prime times y2 plus u2 times y2 prime. So if you guys are getting bored of doing the generic product rule, I'm not surprised, because we seem to do it every freaking time. But check this out. We've got a u1 prime y1, a u2 prime y2. And remember that assumption that I made? This is why I make that assumption, because now that's just going to equal 0. Those two pieces are going to add to 0 because I want it to be. Well, this is going to help us with our derivative, because now we're not going to have any second derivatives of the u's, just the first derivatives. So that means that y double prime, well, it's going to be u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. All right. Well, now let's go and plug those back in to the generic differential equation that we're solving. And let me just write it up here. We're going with the same generic one that we've been doing all this time. Okay, but we're looking at that. So we're going to take the y double prime. We're going to add to it p times the y prime, and then add to it the q times the y. So I'm going to do that. And I'm also going to separate them out algebraically. So if you just kind of take my word for it, so I can spare us a little bit of the algebra writing time, we're going to get u1 times y1 double prime plus p times y1 prime plus q times y1. I'll even show you where all those come from. So the u1y double prime is right here. The p times y1 prime, that's going to come from right here. And the q times y1 is going to come from this piece right there. So that's all the ones with the u1. Similarly, with the u2, we're going to get y2 double prime plus p times y2 prime plus q times y2. And that's going to be this piece, and this piece. So all of those. And then there are still two more pieces. The two that we haven't actually dealt with yet are those two guys. So we're going to get u1 prime times y1 prime plus u2 prime times y2 prime. And all of that equals f of k. All right, but good news time. Look in those brackets. Those brackets are exactly the differential equation. And we know that y1 makes that thing equal 0. So this is gone. That's 0. Similarly, the other set, since y2 was also a solution to the homogeneous, that's all gone. So what we're left with once we kind of get all the way down there, is we now have u1 prime y1 prime plus u2 prime times y2 prime equals f of t. All right, so this is what we know about u1 and u2, is that they're going to satisfy this equation. So there are two unknowns, which means I'd really like to have a second equation that relates u1 and u2, and I've got it. In fact, I still have it on the board. Remember that assumption? That's something else we know about the u's, is that u1 prime times y1 has to equal, or sorry, plus u2 prime times y2 has to equal 0. All right, well, we've got two equations, two unknowns, which means we can actually solve this. So let me turn it into a matrix equation. I know that you guys have seen this before, with the exception of Monty, but this I think will help you guys see what's going on. So here's what this is going to look like. I'm going to swap the order on these so that I've got, well, just because I want to. So my two unknowns are u1 prime and u2 prime. So we're going to get y1 and y2 is my first row. y1 prime and y2 prime is my second row. And what that's going to equal is 0 f of t. So if we just call this guy, say, A, then u1 prime, u2 prime is going to equal A inverse times 0 f of t. So if we can solve this, then we just have to integrate to get u1 and u2. So let's talk linear algebra for a second. What do we need in order for this to have a solution?
It needs to have an inverse, basically.
Okay, so A needs an inverse, which according to your TFAE list, there's 500 million things about it. Right? One is that the determinant is non-zero. Right? Is that going to be the case here? How about this? Do you recognize this matrix?
Yeah, isn't that Wronskian?
Yep, that's our friend, the Wronskian matrix. And what we saw was that its determinant was always non-zero because y1 and y2 are linearly independent. And so since y1 and y2 were solutions to the homogeneous, we know they're linearly independent. Right, that fundamental set, they are linearly independent, which guarantees us we're going to be able to do this.
Mm-hmm.
So that's why I said earlier, this is always going to be possible. Yeah, the integrals may be nasty, because whatever we get from A inverse times this 0 f of t, we have to integrate those two, and that could be hard, depending upon what they look like. However, we at least have a shot. All right, so if you wanted to, you can even say what U1 and U2 are going to look like, because we know how to find the inverse of a 2 by 2. Yeah, maybe, kind of remember?
Mm-hmm.
So if this is A, then A inverse is going to be 1 over the determinant of A times, well, we swap the diagonal, and then we change the sign on the off diagonal. Right? That minus y2 and minus y1 prime. So if we were to put that in, do your magic. Let me just write out what the solution is going to look like. You're going to get u1 prime is equal to negative y2 times f of t divided by the Wronskian. That's the magnitude of A, determinant of A. And then your u2 prime is going to be y1 times f of t also divided by that Wronskian. And so if we know u1 prime and u2, then, and this is, I guess, where we have the drum roll and everything, we get that u1 is equal to the integral of this guy. And u2 is the integral of the other one. So let's go ahead and put a box around those. Because you have now solved every single second order differential equation, linear differential equation. Okay, you guys are definitely not excited enough for that. You've just done every single one. Because all you have to do is take these u1, u2, multiply them by their respective y1s and y2s. There you go, Brandon. I like that. All right, so Wes, what's your dumb question? Yes, you are integrating with respect to t. Or it's either a function of x, then you're integrating with respect to x, or what have you. But yes, I was getting lazy. All right, so good news. Solution always exists. We find them this way. But this is what I was saying, is that sometimes these integrals are such that you can't integrate them, right? Like what if, heaven forbid, one of these ended up giving us an e to the t squared, right? And we're like, well, we're SOL, but the solutions are there. They are these integrals. So mathematically, we know we're good. All right, so let me show you the solution to the example I started showing you as a why we care about this. And we'll see how easy it is to get the solution knowing the solution to the homogeneous. So let's go back to that guy. If I recall correctly, it was y double prime plus 4y equals 3 cosecant of t. And we already did the work to find that y1 was cosine of 2t and y2 was sine of 2t. So the first thing we should do is actually get the Wronskian. Let's build the matrix, find out what that Wronskian is, so that we can put it into these forms to figure out U1 and U2. All right, so our Wronskian matrix is going to have cosine of 2t, sine of 2t. That's our y1 and y2. But then we need their derivatives, which are minus sine of 2t and cosine of 2t. So since it's a 2 by 2, determinant's nice and easy. We're going to get, oh, I totally forgot to put 2's here from our product or chain rule. So we're going to get 2 cosine squared 2t plus 2 sine squared 2t, which hopefully you guys all see is just equal to 2. All right, so we're going to have to divide by that. So let's start with U1. So U1 prime, it's going to be negative y2, so negative sine of 2t, times f, so times 3 cosecant of t, divided by the Wronskian. All right, so there you go. So it's just y2 times our function divided by the Wronskian. So we need to integrate this. Obviously, you can just use your technology, but let me show you why you want to use your trig first. Remember identity for sine of 2t? You should. We really like it. It's 2 sine t cosine t. So here, the t's are going to the 2's are going to cancel. Sine times cosecant, those cancel. And we're left that this is just minus 3 cosine of t. So it's really easy to get U1 then. U1 is just the integral of that. So U1 is 3 minus 3 sine of t. All right, so there's U1. So U2, same process, just we have a different setup for it. U2 prime, that's now going to be U1, or sorry, Y1, so cosine of 2t times f, so 3 cosecant of t, divided by 2. So let's use the double angle identity for cosine to help us out a little bit, because this is 3/2 cosecant times 1 minus 2 sine squared. It's one of the many forms of cosine of 2t. But this is just going to make it a little bit easier to integrate. So we're going to get 3/2 cosecant minus 3 sine of t, because the cosecant cancels with one of the sines, and of course the 2's cancel. So now we integrate this thing, and we get U2. I'll actually write it up here. I just need a little more space. So the integral of cosecant is the natural log of cosecant minus cotangent. And it's totally cool if you don't remember that, and don't worry. And then the 3 sine, that's going to give us a plus 3 cosine of t. And now we're going to get our particular. So remember how we're forming our particular is to do u1, y1 plus u2, y2. So here you go. Our particular yp is minus 3 sine of t cosine of 2t plus 3/2 natural log of cosecant cotangent, sorry, minus cotangent, plus 3 cosine of t, and then that's all multiplying sine of 2t. And I'd be willing to bet a significant amount of money that none of you would have guessed a form like this for a particular solution. Well, except for probably Wes, because you know he's a genius like that. But obviously, no, we would have had no possible inclination that that's what this would look like. But now we've got it. So obviously our y is going to be the sum of this plus c1 cosine 2t plus c2 sine of 2t. Whew. All right, well, there's variation of parameter. So we'll do more of this next time. Don't worry, this was just one example. I wanted you to see the process. And most of our time was actually spent building the process. But now you see why it works. Hopefully even more you see that it always works as long as you've got the fundamental set. So if we can find the fundamental set, which is all, I mean, that's still a big if, right? If we can find it, then we've got a way to find our particular solution, which means then we're done. All right. Okay, so I think this is a good place to pause, and we'll pick up this, run with the same idea here, the variation of parameters next time.